Good morning, everyone. Thank you for joining us. Just so you know, there are going to be a few stragglers coming in. We hear reports of traffic in the Bay Area, and so everyone's transit time to get to the conference center has been somewhat more variable than expected. So we'll expect people to come into the room, and the door will be open, but there'll be no noise, so we're fine with that. So we'll get started, and we'll see what happens as people come in. There will also be a transcript in real time that you'll see on the wall at the back on the screen. So thank you very much for all of you for coming. My name is Paul Borrell, and I've been in the storage and computer industry for a very long time. I like to say that I have 3 careers. My first career was designing processors and memories and cache coherency protocols at Sun Microsystems. And my second career was in the storage industry, into storage software in particular. And my third career was in networking. And so I feel like I've had 3 completely, entirely different areas of technical exploration that I've thoroughly enjoyed. And the accumulation of all of this is what you're seeing today. Some of the skills and the expertise on the stage is world class, and I hope you're going to enjoy the conversations that you have. So let me tell you what the format will be. First of all, I'm going to have the speakers introduce themselves, and then I will start posing some questions in a rather interesting fashion. And we will see what the interaction is. This is intended to be a live, very not just intentful, but interactive debate on the state of the storage industry and what the future might look for us. And then after that, we're going to invite the audience to ask questions. So feel free to ask any question you wish. Please go to the microphone when you do go to ask questions, and we'll be able to get that on the recording, because this is being recorded on video and on audio and on the transcript service. So this is going to be a historic event, I hope, and people will talk about this conversation in the years to come at FMS and other places. So it is now 8:33. I'm going to ask each member of this on the stage to introduce themselves. So let me ask, let's go to the far end and start with Alex. Alex, unfortunately, comes last because his last name is at the end of the alphabet. So I tried to be fair and mix things up a little bit. So, Alex, you get to go first.
Thank you, Paul. Can you all hear me? Yeah. Thanks so much for making this your first session of today. I mean, 8:30 getting here is challenging. Paul said there are reports of traffic in the Bay Area. That's news. So again, welcome. Alex Saprinsky. I am currently the chief technologist for the storage part of HP Hybrid Cloud. I've been doing this for 3 years now. Prior to that, I did some additional technology jobs at HP, mainly focused on storage. Prior to HP, I spent an inordinate amount of time at a great storage company. It's called EMC, and I left just before they became Dell. Make of it what you will. And basically, the storage world is changing. It is changing to a point where it is becoming unrecognizable, and anybody who wants to reminisce about what storage used to be doesn't need to go far. Go and visit the Computer History Museum in Mountain View. There is the first mass storage device ever built by IBM. It can do 2 IOs per second. I kid you not. So we've come far, but we have not come far enough, and I think we'll share some thoughts of where we need to go. Thank you.
Yeah, hello. My name is Sven Oehme. I'm DDN CTO. I started my career at IBM. I worked there for over 20 years, had lots of different roles, Linux Technology Center, worked very early on distributed storage. I'm with the DDN executive team for the last 8 years, and I was pioneering and starting the work on our latest product called Infinia, which is a very high performance object store and data management system. I'm overseeing the strategy of the company and working with a lot of our key accounts to make sure that they have very efficient implementations of their systems.
I'm Michael Kagan. I'm NVIDIA CTO right now. Started my career at Intel Israel, where I worked on the 387 MAT coprocessor. So some of you are young enough to even don't know this. At some point, the computing engine was outside of the main processor. And the reason I mentioned it is because when we tested the 387, we got amazingly high volume storage device, disk server, which was 1 megabyte. So we have done quite a long. Then I was architect of the 860XP vector processor that actually was very fast, much faster than the 486, but Intel didn't put enough software support to it. So my lesson was that chips without software is actually not more than expensive sand. They go away. Then I managed Pentium MMX, which was the first x86 CPU that changed the instruction set. And after that, I moved to start Mellanox, which was the high performance networking company that we have developed products and technology, commonly called today RDMA, that was a breakthrough technology that enabled actually the cloud and AI data centers. At some point, NVIDIA acquired Mellanox five years ago, and I became CTO of NVIDIA, focusing mainly on the AI factories data center architecture. And for me, it also sort of circling back to the vector processor technology, but this time with a lot of software support and tremendous market success. So that's what I am.
Hi, I'm Hannah Early. I'm the CTO and co-founder of Vair Computing. My background started in academia when I was looking at what can science, all the way from biochemistry to physics, tell us about how we might want to build the computing architectures of the future, and what are the fundamental limits of what we can do there. And as a consequence, I ended up kind of through a mutual friend who was part of my thesis committee, meeting my co-founder, and we started Vair Computing, trying to see whether the CMOS that we have today, are there ways that we can make it far more energy efficient and get new scaling laws that take us into the decades to come. And so my hope is that not only will this make compute better, but potentially we can improve networking with this as well.
Good morning. I'm John Colgrove. I'm the founder and chief visionary officer at Pure Storage. I grew up in New Jersey, where I picked up the nickname Cos because nobody can say Colgrove. They all say Cosgrove. So feel free to say Cos. And, I've been doing storage stuff for quite a while. I was at Veritas, where a friend and I worked on the Veritas Storage Foundation for 20 years before I started Pure. And I really, at Pure, am focused on making sure that we destroy all the disk drives. It's a 70-year-old technology. It's time for it to die and be replaced by better stuff. And that's kind of one of the main reasons why Pure is in existence, which means all the disk drive companies hate me.
Excellent. All right. Excellent. All right. Sounds very good. We're into a good takeoff right now. I'd like to tell you more about the theme that we've been talking about in our pre-meetings for this particular CTO Vision Conference. Everyone is aware of the crisis and energy dissipation in data centers today. So a good example here is it's artificial intelligence. As the workloads grow exponentially, and energy consumption has become the paramount challenge in data center operations. In just April of this year, the International Energy Agency projects that electricity demand from data centers worldwide will more than double by 2030, reaching approximately 945 terawatt hours, which is the size of Japan's electricity grid. Isn't that amazing? So NVIDIA's Del Dali highlights that while a floating point operation requires only about 20 picojoules, reading 64 bits from DRAM It consumes approximately 1,200 picojoules when you try to move it across the data center. This is a 60 times distance. So this is just reading from DRAM, I am sorry. Similarly, moving data across racks and interconnects now dominates energy budgets, especially in AI training clusters where over 80% of the power may go towards memory and communication rather than compute. So we have a crisis on our hands. What can we do about it? The nice thing about the crisis is it's a terrible thing to waste. And I'm sure that the incredible creativity and genius that you can see on the stage here will be working furiously behind the scenes. So what I'm going to do here is I do have a list of questions, but I'm hoping the audience is going to beat me to it with good questions. But let me kick things off first of all to find out what the current sense is today, this day, the August the 6th, Wednesday, 2025. What is on their minds? What is it that they would love to have? So I tried 3 times yesterday to go and find myself a wizard outfit and a magic wand. So you just have to pretend I have one. So I'm going to take on the role of being the wizard, and I can grant each of you 3 wishes. And since I'm the one that is the wizard, I can make up the rules too as I go along. The first rule is you can't ask for more wishes. And the second rule is you can't ask for more customers for what you already have. Now, given that as a set of rules to get started with, who would like to go first in telling us what their first wish would be? Alex.
I'll go first. So again, you can't ask for more wishes. That's a bummer, and that's a send-off to the 70s. Anyone played computer games? That was a very interesting paradigm. But coming back to the topic, one of the things I would like to be able to do as a storage technologist is to perform less I/O. And that's an extremely controversial topic. People say, well, speeds and feeds used to be the dominant factor of all the storage systems. You read the storage spec, that's what people care about. How many IOPS, how many gigabytes per second, how much stuff can you deliver? Well, we can't deliver any more stuff. I mean, we can, the speeds are growing, but it's not sustainable from a sustainability point of view and also from pure processing point of view. What we need to do is, I would like us to try and get to a point where the input-output operation does more than just input and output. When you perform the necessary input and output, you also perform transformations on the data, which it either enrich or extract information, and this will solve multiple challenges on Paul's list, which will come up later. So that will be my wish.
Okay, we don't need to go into any particular order. So who would like to go next?
Okay, go ahead.
Oh, thank you, Sven.
Ladies first.
So my wish would be that all of the things that we have learned over the last century or so since Turing and Church started developing their theories of computation, everything we've learned, not just in computer science, but beyond, I wish that we knew this back then, at the very beginning. Because over this century, we've learned so much, but we've also baked in a lot into how we've developed computation. I mean, as an analogy, go back to the choice between electric and petrol-based cars at the beginning. And we made one decision, we went down the route of petrol cars, and now we're trying to go another direction with electric. But you look in computer science and computing, some banks are still running COBOL, the way that we build CMOS is arguably not as energy efficient as it could be, and there's so many different things that we could improve. But it's very difficult to then change from where we are now because we've got these huge industries that are predicated on not wanting to change software and algorithms by very much for very reasonable, for very understandable reasons. And so if we knew what we knew now back then, I think the world would look very different in terms of computing and networking and maybe beyond.
Very nice.
Okay. My wish is that we need to, and I will start a sort of controversial statement that there is no energy crisis. The crisis is of distribution of energy consumption. Because where we lack of energy, there is a few places in the relatively few places on the earth, while there is a lot of other places where the energy is available, be it solar energy or ocean energy. We just don't know how to convert this energy to something more, something useful. And it is loosely ties or relates to the comment that Alex made, is that one of the ways to do it is converting storage from data storage to information storage. So when I retrieve something, it's not just plain bits of data, but something more useful in the information. And this can be actually data converted to information in some other places where energy is more available. So back to the energy crisis, it's not crisis of the energy per se, it's crisis of where do we consume and how do we consume the energy.
What's your wish?
My wish that if we figure out and start working on how to distribute this energy consumption in a way that it will not be energy crisis, but taking advantage of available energy that we don't consume right now.
I think I'll make my wish fairly simple. I'd like to suspend the laws of economics so the best tech wins. I think we've all, during our careers, seen times when a better technology doesn't have the economic scale to compete with an existing technology, and it falls by the wayside. And so I'm not saying the most expensive tech wins, I'm saying the best tech wins. And I think we'd have a more interesting world in that case.
So one of my wishes would be, there is a way to also address some of these problems by simply looking at how can you do much more with significantly less. And I think that is also a problem that we're seeing in the industry, that there's a lot of different options out there, but a lot of people look a lot for speeds and feeds, which is obviously very important, but there's also a very significant portion of where you could save things by just getting more density or less port counts or doing basically more work with just less equipment involved. And if people would focus more on that, that would also solve a lot of the problems.
Go ahead. Oh, it's the second wish time. So the second wish, again, I'll try and keep it tactical, but maybe it will expand. I wish people, and by people I mostly mean infrastructure designers, but also the users, will recognize that sustainability is just not a metric of the cost, it's an architectural tenet. What we used to have initially, okay, maybe there is no problem, we'll just cool these things more efficiently. Then step two, yes, we have a problem, well, maybe we'll just make it run slower and everybody will be okay with this. Well, guess what? People are not okay with this because they want more out of the infrastructure they pay for. Number three, well, you know what? It costs a lot. Maybe we'll have someone else to pay for it, and that's where the carbon credits come into play. And some people actually believe that carbon credits equal sustainability. They do not. It's making Peter to pay Paul. It is about it's an architectural tenet. Design a system that is sustainable end to end. It's not just about electricity. It is about manufacturing those devices. Manufacturing storage systems costs money, takes energy. Then you run them. Then at some point they reach the end of lives, you need to replace them. They need to recycle them. Recycling that stuff also costs money. So it's not just about how to make things consume less power. It is about how to make your drives live longer. It is about how you consume less power in the networking. It is about a core architectural tenet, not just a cost metric. And once people realize that, we'll be able to design for sustainability the same way we design for performance and not as a matter of fact.
I guess we'll continue the pattern. My second wish would probably be that we can jumpstart to far more advanced manufacturing. We can see different technologies that are coming, and a lot of these are limited by what we can do right now. And we can already do amazingly complex manufacturing. The fact that we are doing lithography at the nanoscale and maybe even beyond is kind of ridiculous, but there's still so much further that we can go. We can start to manufacture far better in 3D. And we're starting to explore different ways to do that, but it's very limited and very expensive. And so my wish would be that if I say I want this arrangement of atoms in this 3D volume, that a way to just do that will exist. And I think that will, and to do it in a cost-effective manner. And at scale. And I think that if we can do that, then a lot of the interesting technologies, it doesn't solve every problem, but it allows us to explore these interesting technologies a lot more easily and quickly.
Yeah, my wish is that we figure out how to learn about the world through what we can do with the advanced technologies today, which is simulations or whatever it is. If you think about this, that's the way we learn physics, is we basically observe what happens around us and draw some conclusions trying to generalize this. So it would be cool if we figure out how to automate this process and take advantage of the forthcoming technologies to actually learn about the world and understand it better.
I was going to break the pattern.
I'm going to break the pattern then. Yeah, so it was actually a very good point that you just made, and I think a lot of this has really to do with getting more data management systems that can actually operate with metadata at massive scale. Because I think this is one of the biggest problem overlooked in storage, and it kind of goes a little bit along with your point as well. People over the last decades have primarily, when they talk about storage, they're talking about data. I'm moving bits and bytes in and out. Well, if you would know exactly what those bits and bytes are, maybe you can significantly reduce the amount of data that you're moving around. If you would have better ways to describe what to actually look at, and you can leverage this in the entire I/O path, you can significantly reduce the data that's going around. And one of the things that is actually holding back is that the storage industry in the past has focused primarily about moving bits and bytes around instead of storing significant amount of metadata. So if you have a system that can handle, potentially millions of metadata attributes per set of data that you store, you can much more finer define and describe what that content actually is, so that you don't have to open, let's say, a million different things to look at them to find the information you want. If you look at it one time and you can store back, hey, all of these million things, 1,000 of them contain cat pictures and the other 1,000 contain cars, and then you only care about cars, you say, hey, please give me the pictures that contain cars. And you open 1,000 instead of going through a million to find out which one have cars. And so I think the future of storage is also going to be around being able to massively store metadata, be able to leverage that metadata, and have what I always called context-aware I/O, where basically applications are very aware of the context they operate in and what data they actually have to operate with.
Alex, would you like to chime in on that?
Yes, please. I just can't help myself, so I'll break the pattern once again. This is a great point. A friend of mine many years ago said that any amount of user data can be compressed to 1 bit as long as you have enough metadata to describe that bit. So there is a point there, actually. The point is that we used to store user data. In fact, for a while, storage systems tried to minimize the amount of metadata we can contain because that was parasitic storage. That was something that the user paid for but never got anything out of. Now the trend is reversing, and hopefully we'll break the Shannon laws and get to a point where we have 1 bit with enough metadata describing.
All right, and I'll phrase that in the context of a wish, because, when you store data, the big thing is how valuable is it going to be? What's going to be valuable about it? Right? I could store billions of pieces of metadata about a photo, and really there's only like 10 that matter. So I wish I could know in the future what's really important about each piece of data, and thus store the metadata that helps me access what's important properly rather than have to do bulk accesses.
And I think actually the store part is important, but I think much more important is retrieve part. When you want to retrieve something, you want to retrieve information and not data. And when you store whatever you store, mostly metadata with one bit of real data, this can actually be done sort of slowly, lazily in the background, and so on and so forth. But when you retrieve something, you need to retrieve information and not data.
Okay, have we all had 3 wishes yet?
Just 2 each.
Pardon?
I think we've just had 2 each.
You have just had 2 each. Thank you for helping me keep count. I tell everyone I'm a mathematician, not an arithmetician. So I do need to be judged by people who are better arithmeticians than I am. So let's go. Let's continue. Who would like to go with their 3rd wish?
I will give my 3rd wish, which is even bigger than the 1st wish of time travel and the 2nd wish of arbitrary manufacturability, which is that if space currently is pretty Euclidean, right? Like you draw, you know, in geometry class, you draw some axes. You know that you can move 1 unit up and 1 unit across, and the area between is 1 unit squared, and add another axis and it's 1 unit cubed. If we had, and I guess we don't really know what the geometry of the universe is fully, but if we had very hyperbolic geometry so that effectively space grows exponentially, this could almost solve a lot of the networking and energy dissipation problems that we encounter. You can start to maybe not get all the way to all-to-all networking in an arbitrary kind of cluster, but you can get a lot closer to it than we can today. We're very limited when you're building an AI data center, and you've got you've got your rack level, you've got the units within that. You can maybe get all-to-all with a good enough distribution network in that rack, but then going between just every level up the hierarchy, you're getting more and more congestion, more and more complexity. Hyperbolic space would get rid of a lot of those issues.
Okay, who would like to go next?
I'll just be real simple.
No,
I wish that I could get rid of all the cyber attacks out there so I don't have to have people bugging me about that, and I can just focus on people who actually lose their data through either physical disasters or they accidentally destroy it rather than all the wonderful cyber criminals.
Yeah, well, ideal world. My 3rd wish is, we have physics, which is experimental science. You can try something and then you can try something again and learn about it. What my wish is to make history to be experimental science. So you can actually simulate what will happen in the world after some action and then decide whether you want to take this action or not. Some of the things are being done today already on small scale with the climate. But I would like to see history to become experimental science so we can simulate the world.
So someone mentioned the word physics. That kind of triggers me a little bit because there is something interesting in physics that we can use to try and understand how to manage energy dissipation. So I'm going to ask Hannah if she will give us a description of Landauer's principle because I'm sure that most of us haven't really heard of it before, or if we have, probably not understood it. And Hannah is a world expert on Landauer's theorem.
Thank you, Paul, for the very leading question. What is Landauer's principle? It kind of was a bit of an undercurrent that I didn't explicitly mention in some of my wishes and earlier answers. But Landauer's principle addresses a very age-old question, or, well, depends what you mean by age, but at least back to the 1860s when people like Maxwell and Boltzmann were first thinking about what is heat, what is energy, what is thermodynamics. And one point that Maxwell got stuck on in the 1860s, and so he left a thought experiment. He didn't call it this, other people called it, but it ended up being called Maxwell's demon. And the idea was that, and he maybe didn't know to express it in these terms back then, but the idea was that if you could compute with arbitrarily little energy, then, and there's a little bit more to it, but maybe if you applied this, so the agent was this kind of demon with infinitely keen eyesight who could track atoms, could track molecules, and could kind of control like a tiny door to let atoms and molecules move in certain ways. But the idea was that if you could do this with basically zero energy, you could in principle break the second law of thermodynamics. And this is a problem. You cannot break, or unless someone wishes it, you cannot break the second law of thermodynamics. And so it wasn't really until actually a century later, you could argue earlier that maybe Szilard or von Neumann stumbled across the answer but didn't publish it properly in the 20s and 40s. But in 1960, someone at IBM, Rolf Landauer, published the solution to this, which was that if you want to try to erase any information, and it turns out that the way that we currently build computers has this sort of baked into just the very way that we're using transistors even, that they kind of throw away information on each clock cycle. If you try to do this, then at minimum, every bit of energy that you're erasing, and I say erasing in quotes because physics does not allow you to throw away information, but if you try to, it forces you to do something thermodynamic. It forces you to convert a certain amount of energy into heat that you can't recover. And the very lower bound of this is what Landauer's limit is. And back when this was discovered, this was a tiny, insignificant amount. It's 10 to the minus 21 joules at room temperature. And so back then, we were orders and orders of magnitude above it and had plenty of energy, and that was not really the constraint. And so in the 1980s, Feynman was asked about this, and he said, oh, we're millions or billions of times away from this. It doesn't really matter. But if we got switching energies down to maybe 100 times Landauer's limit, which is about 0.5 to 1 attojoule, depending on how you calculate this, at that point, it starts becoming really relevant, because if you lower switching energies below that point, you lose the amazing reliability of digital computation that we currently have. So, you want to have a chunk of silicon with 1 billion transistors or more, and you want it to not make any mistakes in a couple years of runtime. If that is your constraint, then that's kind of the switching energy minimum that you need. And we're actually really close to that. There are a number of reasons why different laws, Moore's law and other laws, are starting to stall, but this is one of the big ones, that we're getting so close to that switching energy that there's not very much more we can do to make computers more energy efficient. And so Landauer's limit is the reason for this, but it's predicated on this notion of trying to erase information. And because physics doesn't let you do that, you're moving the information just into the environment and forgetting about it. And you actually don't need to do very much. Some might argue you need to change software. There are lots of ways around that. If you change how you do this computation at that, just a little bit at the transistor level, it's an architectural change, but not a huge one. You can start to go below that limit that counts for conventional computing. And in theory, there's no lower bound on how energy efficient that could be. There's a lot of engineering challenges, and that's what we're doing at Fair Computing, trying to kind of push below, not Landauer's limit yet, but just below the switching energy limit for conventional, and hopefully start to get a new scaling law with that. But the consequence, if you can do this, is that not only do you make compute far more energy efficient, but it lets you change how you architect computers and large aggregates of computers. So as Paul was saying, Bill Daly's quote, so I'm not going to do it verbatim, but is that a floating point operation costs 20 picojoules, give or take, and the energy to move information from D around there is then orders of magnitude above and orders of magnitude above even that when you're thinking at the data center scale. So if you can make compute much more energy efficient, this lets you re-architect data centers. Because why do we have data centers as big as they are? You take if you take all the silicon in a large data center and just place it all next to each other, it would fit on this table. So maybe like a cube or something. So why do we spread it out? It's because of heat. And that then leads to complexities with networking and routing, because now you need to move information from node to node. And so that's kind of maybe too long an answer to what Landau's limit is and why potentially if you can start doing computing in a slightly more energy efficient way, it might, as a knock-on effect, help to improve the energy associated with moving information around.
So let me ask if, from some of the other folks who are more computer science oriented, what are the other innovative ways to help reduce the energy consumption in data centers?
Well, one of the things that has to deal with the energy consumption is there is quite a lot of work being done that is thrown away. We talked about speculative execution. So speculative execution is great as long as your speculation is right. But if it's wrong, then you just wasted the energy of speculating. It starts from the way we design the processors, be it vector processors or conventional von Neumann processors, and it goes to the networking. We have invested a lot in the last 25 years to make sure that the network doesn't redo what was lost on the network due to some, or corrupted due to some physical bit error rate and the like, or more efficient networking, which has to deal with the way we spray packets or do the out-of-order placement. This is what actually RDMA technology solves. Another thing is when you move the data from one place to another, you're better off moving it from real source to the real destination and not copy it many times around, which is yet another waste of the energy, and it has to deal with starting with the basic network technologies all the way up to the way we build our software. So, take it short, just make sure that you don't do the work you don't really need.
So there is another probably controversial part. If you look at it, look at the huge AI data center these days. Storage actually plays one of the smallest part when it comes to the power consumption. The majority of the power consumption comes from the compute part and the networking part, and storage is, distant third. Still, I believe storage can have a very massive impact on power consumption. And we've shown this in lots of deployments with our customers, where we can show if you have more efficient storage, and that goes back to the initial point I made, do more with less. If you figure out a way, for example, to increase GPU utilization and eliminate a lot of waste cycles and idle cycles of GPUs by giving them the data at the rate and speed they actually need it, you can make very, very significant improvements. In fact, we demonstrated at the last GTC event, you can deploy a rack pipeline and you can basically make this 20 times faster with only a third of the power consumption in total by just doing things differently. And so I believe the future is also, and this goes back to some of these architectural issues we're seeing in some of the deployments, people need to think out of the box and look at things differently sometimes. And if you take different components and make things more efficient, that's a very, very good way to actually reduce power consumption as well.
So Michael raised the issue about speculative execution. I remember doing quite a lot of work of that in the 1990s with a VLIW processor. I did not realize at the time that it would have such an impact on power dissipation as it does today. But what about networks? Michael, what's your opinion of packet spraying, for example?
Well, the packet spraying is the way to make network more efficient, and whatever it make more efficient is always comes with the power advantage. The packet spraying, the challenge is that you have your algorithms or your interfaces of the network, not algorithms, but interfaces of the network that assume in-order delivery, and that comes with the very old days of the TCP, which is software-defined, the protocol that is designed to be implemented in software. and assumes an order delivery. But when you do the packet spraying, your in order delivery breaks. And actually, it turns out that we can develop algorithms, high-level algorithms that don't really need the in-order delivery. But if we go to the conventional networks, then you basically do this waste of assuring in-order delivery that nobody actually needs. So what we are doing now is we are evolving the protocols, network protocols, and the network storage stack, software stack, to enable this packet spraying without breaking or adding additional cost of hardware and software to make things in order to deliver it to somebody that doesn't care about the order. So packet spraying is basically the way to use network more efficient. It results with the not out of order delivery, and we just need to take advantage of this instead of fighting it.
Alex, you want to chime in on that?
Yeah, so actually I want to go back to storage and then mention about networking, because again, networking and storage are becoming one. Some people get the reference, but on the storage front, computer science is actually a very interesting topic right now. Storage consumes power. It does. Well, it's a distant third. Well, it's not as distant as it used to be, but it is a third one. But still, you want to reduce anywhere you can. So we dug into this a little deeper, and we found that most of the storage power consumption is during writes. So the idea would be, well, can we write less? And that sounds bizarre, because you write what you need to write. I mean, that's what the customer asks for. But can we architect systems that will actually perform less operations on the media? And there is some fascinating research going on in some of the universities. Some of the newer erasure codes where a transition from one code word to another actually takes into account how many bits you flip to reduce the power consumption while retaining your erasure code properties. I think, again, there are some in experimental stage. I mean, they still only apply to persistent memories that are byte addressable, but this is the direction where we want to go. We want to introduce a technology that actually makes you write less, in addition to all the things you can do at the software level to make sure that you actually don't write multiple copies of your data. For those of you who are storage practitioners, you all are familiar with journal systems. Journal systems are the bane of our existence in terms of power consumption. We all love them because they allow us to recover from certain points in time, but they do cause us to write way more than necessary. In some journal file systems, the write amplification can be 20-1. And then it can actually become 200-1, because then you go ahead and fold your journal because you don't want to consume that much space. So there is a lot to be done, and there is a lot of research in that space.
I think the software there, for journal file systems or things like that, the large-scale data storage that we're using now isn't journaling it through the file system and creating that kind of amplification. But it's, right now, everybody's out there trying to brute force all of the AI problems. How big can I make my model? How many parameters? How many thousands of GPUs can I put in for how many hours against it? And I think you're starting to see, people making announcements about how they've cut the cost of actually running a model, or how they're coming up with more efficient models that will greatly reduce the amount of CPU and storage that we need to put against it. You think back to when we first sequenced a human genome, I think it cost $3 billion. And now I could go and I could spit in a slide and get it for $3. When I can build a new AI model instead of inferences for 1/100th the cost of today, will we make our models 100 times bigger? Or will we just say, you know what, I've got something that's 99.9% as efficient for 1/100th the cost, take the cost savings and cut the power usage.
Which is again, it's true. And AI is a perfect example. So asynchronous checkpointing comes to mind. This is a law of unintended consequences. It was implemented because storage systems could not keep up. But now, essentially, asynchronous checkpointing causes you to write less. So that is yet another way to look at this.
Well, the checkpointing is interesting because of how much that's driving so many of the storage requirements, where, again, you're not saying, I absolutely want to save this particular point in my computations. You're saying, I think something might, worried something might go wrong. I want to keep where I am so I can restart there, so I can branch from there. And that's causing people to write tons more data.
Yeah.
And, as we go to newer storage technologies, generally writing is more energy intensive than reading. And so, when you get off of hard drives onto, any of the newer storage technologies, cutting down the amount of data you're writing will be a big thing in saving energy.
Go ahead, sir.
And so one way of doing this is also, changing the way things have been done traditionally. If you look traditionally at storage, and I'm not talking about media, I'm talking more about file systems and the data layers. Systems typically do lots of read, modify, writes, and so if you do small updates somewhere in a file or in an object, there is a lot of write amplification that happens by doing that. So one way you can address this is if you actually have something that is more aware of the context and what I/O you're doing. And in a perfect world, the system would simply decide, okay, this is data that is simply not worth erasure encoding, and it just replicates it. Or this is data that is big enough to erasure encode, and I have a large number of fault domains of targets, so let me erasure code it as wide or as narrow as I technically can. And so having something that is more intelligent on how you actually persist the data, and you make this aware of the actual I/O context by itself, can make a huge difference in saving energy when you write data.
Okay, thank you. I wanted to save about 20 minutes for audience questions, and so we've got a really great context here and a set of people that you'll very rarely get to ask questions to. So please, everyone in the audience, if you have a question, please go to the microphone and tell us who you are, and first, very briefly, and then your question, and then who on the audience on the panel you'd like to answer it. But let me emphasize, anyone can answer your question. Go ahead, Bill.
I'm Bill.
Any people?
80 people. I'm Bill Gervasi from Monolithic Power Systems, and I know that Paul and I share kind of a passion for power reduction and power analysis. I'm going to argue that we've lost our way in terms of how we do speculation. And I know Hannah touched on that, Alex touched on that. We architected our speculation systems back in a single-threaded, single-processor environment, and we've gone to multi-core, multi-processing. Have we lost our way with speculation? We now have a situation where in order to get 64 bytes to fill a cache line, we're activating 20 kilobytes of cells. When we get to a 4 kilobyte disk transfer, we're using 100 bytes out of that. Somewhere we broke our speculation. So the question is this a good problem for AI? Do you believe we can take AI and apply our access patterns and come up with a new, better paradigm for doing speculative operations?
So the answer is yes.
Yeah, absolutely. You beat me to it.
We actually,
Absolutely.
even today, we started to use AI in designing the hardware, designing the software, and power consumption and efficiency, which is loss speculation is part of an efficiency. That's actually one of the criteria that we ask to optimize for.
Absolutely. And if you like to take a second part of your question, can we use AI for this? Absolutely we can, and it actually links with my third wish, where I wish that people would understand that GPT is not about chatbots, it is about sequence analysis. And there's a lot to be generated out of generative pre-trained transformers than your college essay. And getting input sequences and having AI predict and simulate output sequences is a great thing. Digital twins is what you want, like that's one of the approaches. You can't possibly build all the models and run them, that's not economical, but running simulations using digital twins is probably going to get us a long way.
And on the, I'm not talking about the CPU side. If you look at the data side, one of the most efficient areas in storage is, for example, prefetch algorithms. So a lot of times you kind of overread data, that you actually never consume. So why is this? Because there's typically no context of what that I/O is doing. So if you have a system that goes back to my point of metadata and describing things in a more contextual way, if you would know this particular application opens this file, and every time it opens it, it reads it from the very beginning to the very end. But this other application, if it opens the file, it basically skips every 256 kilobytes and just reads a 1 kilobyte header. If you would have that context, your prefetch algorithm could be much, much smarter because it would only read what it assumes the thing is going to do again that it did the last 3 times. And so the reason you can't implement these type of intelligent prefetching and caching algorithms is because there's not enough metadata stored in modern storage systems, with the exceptions of a few, one of that I worked on, in order to do this. And so I think if we would pay more attention to these type of things, you could, make prefetching and basically speculatively reading of data much, much more efficient than it is today.
Bill, can you test the microphone one more time?
Nope.
Just give us 10 seconds. Go ahead. Try again. Okay, so here's what we're going to do. Okay, thank you. What we're going to do is have one of the panelists, anyone you wish, repeat the question. Speak loudly when you. Please go to the microphone anyway. You speak loudly so everyone can hear it, and then we will repeat the question, or maybe I will. Go ahead.
I'll use my professorial projection to avoid the problem. So you all talked about AI and context. Today, AI is computing with these multimodal embeddings, which are 1,400 floating point wide vectors. And the GPU is the architecture of choice for doing this. But you all are about to add context graphs, like indices and all, to those vectors. Is GPU still the right architecture for working with embeddings and context, given that GPUs today are performing at 1 to 2% of peak teraflops for graph problems like CG?
Repeat the question.
So the question is whether GPU is the right architecture for implementing the modern AI. So the GPU architecture evolving every generation, and we are actually adding more optimizations both on the hardware and the software layer to cope with the new challenges. And the way we design the GPU is that we implement in sort of harder way what we know, and we leave enough flexibility for efficient implementation of things that we don't know. And we don't know what we don't know, but and here is it's a very very tiny path to make sure that on one hand you don't limit yourself in terms of how much programmability do you provide, and on the other hand you don't over-design the programmability, because then you end up with the same situation as the Van Neumann machines today that are not efficient enough to do the work to execute the modern workloads. So we are focusing on the workload, not on the flops and not on the gigabits per second or something like this. We look at the system at different scales, starting from rack and all the way to the data center, and see how can we implement the workloads more efficient, and how can we leave enough room for flexibility and programmability to change the algorithms.
Thank you. Did you get your question answered? Good. Excellent. Next question. Please speak loudly. The microphone isn't working, so you need to speak loudly.
Sure. So my name is Didier Kazansky. I'm CEO and co-founder of SMSonics. We're the company behind developing 5G port class, ultra-durable, ultra-density data storage. And my question is, I think Alex touched upon it, about sustainability of data storage. There's a lot of focus about energy use for the data write and the data read.
The data write and data read aspect, but also there's the aspect of the materials that are used, the actual production, the energy used in the production of the data storage systems, the fact that we're in unprecedented times right now in terms of the amount of data being generated. So could it actually be that there is a bottleneck in the future with data storage, with the materials required to support data storage and the energy required not only to power the data storage side of things, but actually to produce the different devices for data storage?
Good. Excellent. Thank you. Who would like to answer that question?
Yeah, so
Alex, go ahead.
I'll try. I mean, at least I will start. So the answer is yes. And today, as it was said, like we want to get rid of all the disk drives. And the direction where the technologies are going today is to move to like an SSD-like media, where the cost of manufacturing is actually perceived to be lower. But there was actually a very controversial study that I read somewhere that tried to argue that spinning disks is actually more sustainable in the long run because, for example, they're easier to recycle. There are some things that you can take into account. So it is not just about manufacturing it. There are literally 3 steps to sustainability. So step 1 is how do you manufacture this, step 2 is how do you operate this, and step 3, how do you get rid of this? And all 3 of those need to be accounted for. The way I see it, it's not a one-answer problem here. And I think this is a major one in the industry. Sustainability is a central architectural tenet. It is something that we need to look at end-to-end. Something that we're learning to do. I mean, it's not coming natural to us because we as an infrastructure providers build stuff and then we believe that our responsibility has ended. Now it's somebody else's problem to operate it and the cost doesn't come out of our pocket. So why would we care? I mean, we need to care because you need to get the Energy Star or some other checkbox that your solution addresses it. We want to be good citizens. We want to be energy efficient. But I think sustainability is an end-to-end problem, and the sooner we wrap our heads around it, the better. I hope I answered your question.
Yes. Thank you very much.
Okay, good job. Next question, please.
Curtis Ling, Max Linear. Thank you for the great panel, even if you did propose violating the laws of physics a few times. One way to look at LLMs, or what we have, is that they are tremendous compression engines. So you give it a very small query, you choose your model, and out comes quite a lot of, most of the times anyways, accurate, useful information. So you can think of the models as a priori or shared information. And as they get larger and larger, our shared information gets more and more. And furthermore, notwithstanding our violation of privacy, the network or the computers know more about us. So they have a lot of a priori knowledge as well. So then the storage, so that then intention can be accurately assessed, and all this accurate or plentiful context becomes your a priori knowledge, and therefore your compression can be extremely efficient. And therefore all the things that you talked about, which is avoiding unnecessary network communication, avoiding unnecessary storage of information, all that becomes possible. Could you please comment on this?
Well, let me start at least. And it was mentioned multiple times in sort of different ways. Is that storage is not just storing the data; it is being able to retrieve information. My view, for example, is that there needs to be much more computing capability in what we call today storage devices to enable this processing and preparing the information out of the data that is dumped there. LLM is part of it. you can use AI models to do this inside the storage server itself. You can make this data pre-processing to work in confluence with what is going to be used for. So you need to understand what is it for, and it's going back to the metadata and some additional information that is stored there. So that's my take.
Thank you.
More
Next
computing
question.
in the storage.
Hi, Sam Carter, IG Capital. We invest in semiconductor startups. I'm curious for everybody on the panel, what's one technology or feature that exists today that you wish more people knew about?
So, I don't know exactly that I wish more people knew about it, but I wish more people did a better job of properly doing long-term preservation of data. Data archiving has just fallen by the wayside because people don't like dealing with the old technology, and the new technologies haven't yet gotten to the kind of economics that promote it. And you think about it. You want your doctor to have your medical data as far back as, from when you were born. All the government records, financial records and things, they need to be preserved much better than they are. And, it's something that we've neglected because it's the non-sexy part of the industry. So I wish people did better at that.
Anyone else want to take a crack at that answer?
I guess sort of a selfish answer to the question, but I wish more people knew about adiabatic reversible computing, this technology that's been around. Well, the last time it kind of, if we compare to like AI winters and AI summers, the last time we had a summer was in the 90s, and had pretty long winter, but if our recent results are to be believed, I would say that this technology is now actually feasible and very relevant to current workloads. And so I wish that, not that I want to spawn competitors, but I wish that this was more of a well-known technology, and maybe we start to think about, not just for the years to come, but also for the decades and centuries to come, as we start looking at more advanced computing architectures. What might those look like when we take into account technologies like these?
Excellent question. Thank you. All right, so we've got a couple of minutes left, and then it's time for the break. What I'd like to do is leave this question open for each member of the panel to answer in their own way. So the question is, what is your vision for the future of memory and storage? Alex, go ahead.
Okay, I'll start. Thank you. It's a loaded question. My vision for the future of memory and storage, that they will become one. Basically, the boundary between memory and storage is blurring nowadays. We used to have a very, very distinct differentiation between memory and the mass storage device, so to speak. But then again, as I mentioned earlier, there was a wonderful machine built by IBM in the 1980s. It was called AS400. Today it's called I-Series. It's still out there today. They introduced a concept where, from the user point of view, there was no distinction. The system had something called a single-level store, and the user of the system didn't care whether the data was in memory or a mass storage device. It just was. So obviously the operating system developers cared because the technology was somewhat different then. I would like us to get to a point where we reach an architecture where a distinction between memory and storage is blurred up to that particular expensive piece of sand that's called the silicon, and it's hidden from as many people as we can. Yes, properties are different, attributes are different. Data that is stored for longer times has different attributes, cost-wise, performance-wise, longevity-wise, than data that's stored for computation. That is all true. That is unlikely to go away, but I think I would like not to know, or know as little as possible, to simplify the overall system architecture. Again, simple for the user doesn't mean it's simple, but I would like to make it simple for the user. And again, us as the infrastructure developers, we would like to be good world citizens. We're trying to be good world citizens. We're investing a lot in sustainability. Sustainability is not just consuming less power. And this is where I think we need to go with memory and storage. And I hope it made sense to you.
Sven, go ahead.
Yeah, I think there is a couple of technical challenges that people run into today with this. So I agree, it would be very beneficial if it would be just one. But I think just take very basic things like you operate on a file system, you have your own process that allocates its own memory. Even in simple things like that, memory even is not necessarily shared amongst all the different players that participate in a total pipeline end to end. So I think the answer to some of these problems is going to be exposing very rich APIs and allowing you to basically link different layers together, so it becomes much easier for the end user to operate on the data. And you don't really know exactly, is this now kept in memory, is this now kept on whatever disk drive, or is it kept on NVMe or whatever media, because that's another trend we're seeing. We're actually introducing more different layers and types of memory as well. And so that is, actually going kind of the opposite way. We're making it much harder now. And so I think one of the way to solve that problem, as I said, is provide APIs that people can link into the application where the complexity is hidden by the software development kit that provides these APIs, to basically take the best use of memory versus NVMe versus whatever media you're storing.
My take here is that I would like the memory and what is called memory and storage today to become the data platform that delivers information people are looking for, and figures out how many bits and what bits it needs to keep in what form, be it in the LLM model, which is weights, or some plain data. But it is basically the AI data platform that delivers information on retrieval.
My vision, you could almost argue, built a little bit off of Alex's vision. So Alex's vision combined memory and storage. My vision is you combine those with compute, and eventually what we now know as the data center is a cube or a sphere, pick your favorite geometric shape, but a cube of compute. We're already starting to see this a little bit today, in very early stages when you look at reticle size dies, where we're kind of integrating a lot of SRAM. Maybe we've got HBM, maybe we've got other things that are moving the memory close to the compute. We're still not currently, or we're struggling to place logic very close to HBM. Usually the HBM and the logic are next to each other with 2.5D packaging. There's interest in 3D packaging where you put the logic die underneath the HBM. But imagine if we didn't have to keep all of these components and separated enough for thermal considerations. If you could thoroughly mitigate thermal considerations, at least to a significantly greater extent than today, you could really imagine, in the near-term future, having blocks of compute and memory all together in one, and in the very long-term future, all of these sci-fi notions of Jupyter brains and Matryoshka brains could perhaps even become a reality. So I think we're already taking the first steps towards this, but I think there's a lot further we can go.
So Johnny, looks like you get the last word.
Yeah, after all the good answers you're taking. I'm actually going to build on the sort of combining of storage and memory and extend it to all the hierarchies. When I'm storing data very temporarily or when I'm storing it long term, right now I have to do a lot of work in how I set up the system to have the data stored the right way that makes sense for that use. And a lot of coordination, and a lot of times you sort of miss data as you move it from one to the other. So I'd love to see more of a seamless system where, yes, I'm storing the data, yes, I have certain needs for the data that becomes apparent either from the application that's accessing it or from the way I access it. And it's just like one, one layout, one way in which the data is organized from my standpoint, so I access it regardless of whether it's 100-year-old data or 100-second-old data.
Oh, well, thank you very much, everyone. Let's give the... Okay, thank you, everyone.